Hello and welcome YouTube, Mr. Robbins back here with yet another brand new exciting video, all math-based of course, and as always, it's an honor and a privilege to be serving you here today, as it is every day here in my virtual classroom. Step on inside, let's watch the wildcard game, the Red Sox and Yankees. It's 0-0, goose eggs, bottom first. Let's do some factoring. Let's factor special case quadratics. We've distributed them before. We've taken something that was squared into a perfect square trinomial, and we've taken sum and difference of something and turned it into a difference of two squares. We are now going to do the backwards version of that, and I have 28 practice problems for us to do, which we will be factoring each and every one of them, and the last 6 will also be solving using the zero product property. Now, if you know what you're doing with this, and if you're well aware of multiplication a little bit and your perfect squares, this could be done literally in a matter of minutes. And when I say minutes, I mean the number you can count on your hands kinds of minutes, if you know what you're doing. So this will go on as long as it has to, but I have a feeling it won't go as long as it needs to once we start getting the ball rolling. So let's prep this a little bit first, though. Let's sharpen our axe, if you will, and let's get down to business. I'm going to start by squaring some numbers for you. I'm going to give you a list of perfect square values up to 16 because my worksheet that I generated here only has perfect squares going up to 16. 1 squared, 1 times 1 is 1. 2 squared is 4. 3 squared is 9. 4 squared is 16. And then we keep going. 25, 36. And these are numbers that you want to kind of know. I think for the most part you probably do, at least up to 12, right? And then there are some other special ones you're going to want to know, but here's 11 squared and 12 squared. 13 squared is 169, 14 squared is 196. So those are pretty interchangeable there with those numbers a little bit. 15 and 16 squared, I think you do want to know. These numbers come up enough that they're kind of important. Beyond 16, I'm not saying they're not important, but they are a little less occurring, rarely occurring. These two don't occur very often. I just said they're kind of good to remember, 13 and 14 squared. Then you can use 20 squared, 24 and 25 squared, things like that. But I'm only going to go up to 16. So these are important because what we're going to be doing here, guys, is we're going to be looking at, one second, perfect square trinomials and difference of two squares, where you will be seeing these numbers appear so often, so much so that when I see it, I'm just going to say, when I see 121, guys, I'm just going to say that's 11 squared. Hey, look, 121, that's 11 squared. You know what I mean? So the list won't always be here. Write it down for yourself. Have it in mind, access it, use it, know it over some point. Now, we're going to start, it says factor each special case quadratic completely. These are all special case quadratics on this front page here, whether they are perfect square trinomials 1 through 8 or difference of two squares 9 through 16. And we're going to go ahead and factor these. So let's start with the perfect square trinomials. And the recognition of these is that every single trinomial will have a first term that is squared, or value that is squared. The second term will be double the product of your first and last value here, and the third term will be your third value squared. And this factors into a plus b quantity squared. Now, if this is subtracted here, then this will be a minus b quantity squared, and I've referred to that with my classes as well. So this plus or minus says that if this is a plus, that's a plus. If this is a minus, that's a minus. So our recognition of what those things are will allow us to know what this factors to. Now, when you look at number 1, I do understand that you could do your whole diamond, what two numbers multiply to make 16 and add to make 8, but understanding it's a special case quadratic to begin with is kind of nice in saying that, all right, well, I can recognize that this is also something squared. If I square n, I get n squared, of course. If I square 16, I get 4 squared. And the only question that remains here, which the answer is yes for these because these are all special cases, is 8n double the product of n and 4? Really, 4 and n if you think about that, because you double the 4, really. So yeah, you know, this is your a squared plus 2ab plus b squared. And this factors into a plus b quantity squared. This is n plus 4 quantity squared, like that. Now remember, n plus 4 quantity squared does mean n plus 4 times n plus 4. So if you ever factored this, you found out what two numbers multiply to make 16 and add to make 8, you would probably write it like this. You'd box it and you'd be done. But I want you to really, I want you to recognize these things when they are like this and know that these two things are, of course, equivalent. And the more, I'm not going to say simplified, but the better off answer really is writing this quantity squared like that. And just, again, know that they are interchangeable. All right, let's look at problem number 2 here. Same kind of thing. Yeah, I do have 1k squared. What two numbers multiply to make 121 and add to make negative 22? But if you really do recognize, once again, obviously k squared is k squared, and 121 is 11 squared. So is 22 double the product of k and 11? Or 22k? Yeah, minus being a minus 22k. Just understand that, a minus appears here, and you can say double the product of k and 11 like that, and all's good. You're squared away. An alternative to this, just so you're aware here, like I said, you could put a plus here, but then you just got to make sure that you're recognizing the 11 as a negative number like that. Regardless, you still get the same answer. If you are adding with a negative there, it still becomes subtractions one way or the other. I'm probably going to be writing it like this, if that's okay, minus double the product of k and just that number. So anyway, this is going to be an a minus b quantity squared. So that's k minus 11 quantity squared like that. Or k minus 11 times k minus 11. But of course, I'll be writing it like this here. Now again, you're probably wondering, why are we doing it this way? Why don't we just do it the regular old good old-fashioned way? Because you want to, there are a couple reasons. Number one, we want to be able to know that we can simplify to this thing where it's something squared, that we have to be able to know those squared quantities. You want to know perfect square trinomials in their nature when we start using when we start doing what's called completing the square. That's going to be important. We got to know how to do it there. And furthermore, some of these are going to get very hard and challenging to do if you don't use it. You're going to start seeing them once we hit number 5. Or at least the idea of, you don't want to use that other version of something if you don't have to. But let's look at number 3. Same thing. We are squaring x. And 256 is 16 squared. Once again, just kind of that knowledge. Here's your list. That's 16 squared right there. 32 is double the product of x and 16, right? 16x doubled is 32x. So that is x plus 16 quantity squared. So once again, you can kind of recognize if you know your perfect, so here's the thing, you want to know your perfect square list, so when a number comes up like this, you're like, that's a perfect square, right? That's just something that's knowledgeable, because for these things here, you do want to know that if it is a perfect square, there's a chance that it's a perfect square trinomial, or a difference of two squares, of course. But you'll know that one because of the nature of the problem. All right, number 4, that's a 3. Oh, well, it's not a 1, but oh, hey, these numbers can divide by 3. So if I factor a 3 out of here, which we always look for greatest common factors first, by the way, then you're left with m squared minus 20m plus 100. So we got to factor this inside here. Hey, m squared is a quadratic, right? That's a perfect square. 100 is a perfect square right here. That's 10 squared. And 20 is double the product of m and 10. I mean, 20 is 10 doubled, really, right? That's what I'm looking for. 20 is 10 doubled. I don't care about the m. I know that the m is a part of it. So yeah, this is 3 times, that's m squared minus 2 times m times 10 plus 10 squared. And again, pretty soon I won't be writing all this over and over. It's square the first, square the last, double the product of the two. So that is 3 times the quantity m minus 10 squared, like that. There we have it. Okay, moving forward, numbers 5 through 8, the last 4 perfect square trinomials before we kind of get to some backside stuff here. Now, I'm telling you right now, we know that these are special cases, but we can kind of confirm as we move forward here. 9v squared plus 24v plus 16. First, you try and ask yourself, is there a common factor? There just so happens to not be a common factor, so we're going to have to work this out. And what you would normally do if you saw my last video on factoring things is we'd say, hey, is this 9v times 1v, or is it 3v times 3v? And then you'd have to play with 16. Is it 16 and 1, 1 and 16, 8 and 2, 2 and 8, 4 and 4, whatever like that, and play with them. But if you also recognized, if you do recognize that 9v squared, hey, that's a perfect square value. That's 3v squared. I'm squaring 3v, right? Because the v gets squared, obviously. But 9 is 3 squared. And 16 is 4 squared. The only question that you ask after that is 24v, really, I really care about the 24. We know that a v is there, so the 3. Is 24 the double the product of 3 and 4? Is 24 double the product of 3 and 4? Because if it is, we have an a squared plus 2ab plus b squared. Now, of course, you already know that these are special case quadratics in this set of first 16 problems. You know that they are. You don't even have to question it. So, I mean, I'm questioning it in the case when you have to, but you know that that answer already is yes, and I'm setting it up for you so you know. 3v times 4 is 12v, doubled is 24v. So yes, that does become that. Why do we say all this? Because instead of testing all those other things, if you recognize those are perfect scores right off the bat, 9 and 16, then you can ask yourself, is 24 double the product of its roots right there? So this does become 3v plus 4 quantity squared, like that. And again, what I showed you here is the result of something that we learned in the past when we distributed these special cases. So this is something that's old. If you've been with me before, if you're one of my students, it's something that's old that is resurfacing. So we're taking what we knew from before and applying it in factorization. Okay, number 6. Once again, would you want to play with all the, these are composite numbers here. Thankfully, they're not the worst ones. 25 is either 25 and 1 or 5 and 5. 49 is either 49 and 1 or 7 and 7. But even still, just in playing with them, you probably don't want to do too much in the way of, how do I say it? You don't want to do too much in the way of testing all those values when, if you recognize 25 as 5 squared, and you recognize 49 as 7 squared, then the only question is 70 double the product of 25 and 49? Oh, excuse me, of 5 and 7, I should say. And yes, of course, because 5 times 7 is 35, and then double that is 70 right there. So that does become 5n plus 7 quantity squared. I'm going to state right now that I'm going to stop writing this anytime we see these, but I'm going to say them out loud. I'm going to stop writing them, but I'm going to say them. So let's go to this one, number 7. 225, that is 15 squared. That is 15 squared there, okay? So we have 15 squared on that one, 15v squared, I should say, and 4 is 2 squared. Is 60 double the product of 15 and 2? Yeah, 15 times 2 is 30. Double that is 60. So this does become 15v plus 2 quantity squared. I'm done. I mean, 225 has other factors, guys. It has 5 times, I don't even know, 5 times 40, 5 times 45, 25 times 9, obviously 225 and 1, 15 and 15, and then 4 is 4 and 1 and 2 and 2. There are a lot of different things that you'd have to do along the way there, but I already got it factored from there. And lastly here, 200 isn't a perfect square. So you might be going, uh-oh, I got to do factors of 200. No, you got to, well, if you look closely enough, guys, these have common factors within as well. I can definitely factor a 2 out. I can't guarantee anything else after that. Let's try 2 first and see if there's anything else beyond that we should try. So we have 100x squared plus 180x plus, okay, yeah, that's 81. So it looks like that's the smallest you can factor out there, which is 2. I mean, 100, again, is 101, 50 and 2, 25 and 4, 10 and 10. That might be it. But 81 has 81 and 1, 9 and 9, 3 and 27. A lot of different combinations to play with. But if you notice, 100 is 10 squared and 81 is 9 squared. Is 180 double the product of 10 and 9? Yep, 10 times 9 is 90, doubled is 180. So that does become 10x plus 9 quantity squared. Again, I'm not writing the in between anymore. If you recognize that's what it is, you're good. Boom. That's how fast these can go if you notice what's happening there. That's what I'm saying. It can happen within minutes. Now, I've spent 14 minutes so far, but that's me teaching it, not just doing it. If you want me to do these in time trial fashion, guys, we can have a nice challenge there. All right, now you have some difference of 2 squares. How can I tell? Because it's one thing squared, another thing squared, and you're taking the difference of them. It's only 2 terms. It's only 2 terms. And if there's no common factor, as in a common factor with a variable like a v there to factor out, then you're dealing with a quadratic and a constant there. You're dealing with the difference of 2 squares thing. Now, what is the difference of 2 squares relationship? Well, if you have something squared minus something squared there, it factors out into an a plus b, a minus b kind of scenario like that. So whatever is being squared and being squared here kind of works in that fashion. So I'll write out the first few, of course, and then I'll go without writing them the rest of the way, especially on the back when we get there. All right, v squared is v squared. 9 is 3 squared. So recognizing a is v, b is 3, this does factor into v plus 3, a plus b times v minus 3, like that. Now, if you were, so see, here's the thing. If you're doing this a practical way, you would have to spell out the linear term, which would be 0 v minus 9 like that. And then if I were giving a diamond version, we'd say what two numbers multiply to make negative 9 and add to 0. The only way that's possible here, with that being negative, is one positive, one negative, and they'd have to be the exact opposites of each other. It would have to be 3 and negative 3. I mean, you're spending time doing something that is spelled out in front of you by nature of the difference of two squares setup, that the two terms cancel. They have to be exact opposites of each other. That's why this is what it is, being exact opposites, plus b minus b. So instead of doing all that and guessing, recognizing it's a perfect square is all you really need for that. So I don't want to do all that. I'm going to avoid doing all that. We're not going to have to, especially when the numbers get unnecessarily large. Not unnecessarily large, but we do unnecessary work when it becomes large. All right, number 10, x is being squared and 5 is being squared. I'm already going to stop writing them. So this becomes x plus 5 times x minus 5. And yeah, difference of two squares, I think people are more comfortable doing this kind of setup once they recognize what's going on than perfect square trinomials, especially when, like I said, the middle terms cancel and it's really obvious what it is. But I want to do the first things. I want to do perfect square trinomials first so that those don't feel uncomfortable when we go back to them. I think once you start doing these, you'll feel more comfortable going back to the other ones. N squared minus 196. 196 was 14 squared, so this does become n plus 14 times n minus 14. Again, that's just as fast as it goes. Once you recognize that n is squared, right? A squared plus b squared. That is n squared minus 14 squared. And then lastly, 13r squared minus 468. I would know 468 is a perfect square, not right off the bat. I believe it's not, but I know that 13 is not. So the only way this thing will be of benefit to us is if we say 13 is a prime number. Let's hope it's a common factor of this thing. Let's hope that we can pull a 13 out of here, and we're going to be left with r squared minus some perfect square right here. Now, I don't know 468 divided by 13, so I'm going to use a calculator right here and figure that out. Give me one sec. 468 divided by 13, that's 36. 36 is a perfect square. So that becomes r squared minus 36 with a 13 on the outside. Now, again, 36 is 6 squared, and this is r squared. So this is going to be 13 times a plus b times a minus b, like that. All right. Okay, now we get into ones where even if there is a common factor, we're going to be left with an a value that is not necessarily 1, or it's not 1, I should just say. So 4x squared minus 49, once again, if you can get that recognition of, yes, 4 is a perfect square, obviously x squared is a perfect square, so this becomes 2x squared there. 49 is 7 squared, and that's what we're subtracting. So this does become, indeed, 2x plus 7 times 2x minus 7. Oh, I'm sorry, that's squared. So recognizing that a squared minus b squared gets you into that straight up, where we don't have to do 4x squared plus 0x minus 49 and try and do numbers of here that can combine to do and combine to get the 0. We're not going that far into this, guys. We're just going, you know, I'm giving you a shorthanded process. You might as well take advantage of it when it's there. Recognizing it's important. Knowing your perfect squares is important. Dealing this out is important. This idea, now, I talked about perfect square trinomials being important for certain reasons, including completing the square. That's something you'll do down the line. These are used in what's called conjugation. These two factors are called conjugates of one another, where those middle terms cancel and you're left with, again, a difference of two squares. That's also important to know down the line. So this isn't just shortcut for shortcut's sake. It's shortcut for efficiency for things that you're going to use them for later. This knowledge, this understanding of how these things cancel is an actually important tactic. It's not just a process of a special case. These special cases have and bear meaning to what we do. All right, 81, that's 9 squared, and obviously the b is there. And then 1 is 1 squared, right? So that'll be, when we take that, that's 9b plus 1 times 9b minus 1. I'm going to stop that one on that problem there. That's it. That's what that equals. All right, good recognition. Hey, just moving on forward, guys. These go fast when you know what you're doing. 25 is 5 squared. 256 is 16 squared. Difference of two squares there. This becomes 5m plus 16 and 5m minus 16. I mean, my answer is my work. Technically, that's my work, but I'm verbally giving you the rest out loud. And then 224m squared minus 126. I don't recall those being perfect squares. Must mean there are common factors. 2 is a common factor, but I think, no, 4 doesn't work here. If I factor out a 2, I think I'm still going to be left with some other stuff here. Because that's 63, which would have common factors. Let's dive deeper into this. Let's make sure we know how to find greatest common factors of something that's even larger. I'm going to do the prime factorization of these values, meaning and break them up into their prime factors, and then see which factors are shared. 224, I'm just going to use 2 in my other number. 2 and 112. 2 is a prime number. 112 breaks up into 2 and 56. 2 is a prime number. 56 is 8 times 7. 7 is a prime number. 8 is 4 and 2. And 4 is 2 and 2. So, heyo, 224 is 2 times 2 times 2 times 2 times 2 times 7. 1, 2, 3, 4, 5. 5 2s and a 7. 32 times 7, if you will. 126, let's break that number up into its primes. Let's divide that by 2 to start. That gets you 63. And 63 is 9 times 7. And 9 is 3 times 3. So, 126 is 2 times 3 times 3 times 7. Now, the greatest common factor of 224 and 126 is whatever prime factors are shared and multiplied together. So I share a 2 with both of these and a 7 with both of these. The remaining 2s and these 3s don't share with each other, and 2 times 7 is 14. That means that 14 is the largest value that can divide or factor out of these two terms right here. So if I factor out a 14, I'm left with, I don't know, 224 over 14. I don't know. 224 divided by 14. I should know, but I'm going a little slowly. I think it's, wait, 220, shoot. Did something wrong with my calculator. Give me one sec. 224 divided by 14 is 16. I should have known that. 16, I was doing something else in my head. Is 16m squared minus 126 over 14, I think is 9. 16m squared. Oh yeah, perfect squares also. 16m squared minus 9 there. And hey, 16 is a perfect square, 9 is a perfect square, right? So now that's 4m plus 3, right? 3 squared is 9. 4m plus 3 and 4m minus 3. So there are other ways you can do the common factor things when you're working on that, but you do need to get out the greatest common factor. If you're left with a difference of 2 squares there, you can go from that portion. Okay. All right, so that's the front side there where we're doing the things when we know that these are all special cases. Obviously, difference of 2 squares kind of reveals itself to be a special case. Perfect square trinomials are not always so obvious with them, so that is that front side with that. On the back side, I give you 6 problems here where we determine whether they're perfect square trinomials, and then we factor regardless whether they are or not. Now, a little heads up with this that makes it a little nerve-wracking here. The first and last terms will be something squared, so those things are squared values. The question becomes whether or not the middle term is double the product of those things that are squared. So in a perfect square trinomial, that's what we have to figure out. Once again, if if our thing is some form of a squared plus 2ab plus b squared, or a squared minus 2ab plus b squared. And if it is, then we could factor into this. If it's not, we're going to have to factor using conventional means, meaning something else where you got to break things apart and do guess and check, and you'll see that they just take longer. If this is factorable in that other way, I'm going to write out the factorization immediately. 144 is 12 squared. Let me get these ones out. 144 is 12 squared. 25 is 5 squared. Is 120, this is where the answer is not necessarily yes. Is 120 double the product of 12 and 5? That is the question here. 5 times 12 is 60. 60 doubled is 120. So the answer is yes. That means this is a perfect square trinomial. This is 12m plus 5 quantity squared. I'm done. I recognize this is a perfect square. I recognize this is a perfect square. And then we confirm that this is double the product of those two things. That's what we're doing on these. All right, this one. M squared plus 25, m plus 144. Well, gee, that one actually seems, I guess, easier than this one. If it's that. M squared is obviously m squared. It's 1m squared. 144 is 12 squared. Is 25 double the product of 12 and 1? 12 times 1 is 12. Doubled is 24. Ooh, no, it's not. So this is not m plus 12 squared. Right, that would have been m squared plus 24, m plus 144. That's a different problem than this one. This one is m squared plus 25, m plus 144. So that means we have to factor, oh, I'm sorry, this was a yes. Yes. And this one is a no. This is not a perfect square trinomial, but we still have to factor. We still have to find out what two numbers, because it's a 1m squared, what two numbers multiply to make 144 and add to make 25. Now, 144 is a rather larger number. That's why you're like, oh man, now I have to do this. Yeah, that's the point, is that if it was a perfect square trinomial, you wouldn't have to do this thing. So 144, you can try. I mean, if you try 12 and 12, we already know that doesn't work. But, 1 and 144 divided by 2, you get 72. 3, you get 48. 4, you get 36. 5 doesn't work. 6, you get 24. 7 doesn't work. 8 works. 8 is 18. Yeah. 9, I think works. 9 is 16. 10 doesn't work. 11 doesn't work, and 12 is 12. So those are all your factors of 144, right? That's a lot of them. Positive product, positive sum means plus plus. Which one adds to 25? No. 26. 25 and 20. Look at that. 26, 25, 24. It's 16 and 9. 16 plus 9 is 25. And so those become your numbers. That becomes m plus 16 times m plus 9. Just so you know, I knew this answer a long time ago. It's here. No, you didn't. Yeah, I need to show the process and say, that's what you got to do, right? I'm spending that time on factoring that one there, and you would have probably spent time doing the same thing if this was 24. If you didn't recognize this 24 would have given actually a perfect square trinomial. So if you recognize it's a perfect square trinomial, guys, if this is an indication, that's a lot faster to do it if it is one. I'm trying to give you validation that it is. All right, this next one here, 256. Hey, that's 16 squared. 1. Hey, that's 1 squared. Is 32 double the product of 16 and 1? You betcha. So, but you got to make sure you put a minus here because this is going to be 16n minus 1 squared. And by the way, that one has to be a plus. If this is a minus, we put a minus there. But that has to be a plus for this thing to work. And I'm done. That's it. That's all I'm going to do. You know what I'm also going to do? I'm going to change this color to green. There we go. Okay. So now I'm done. So this next one here, 9v squared minus 10v plus 1. 9v is 3, or 9 is 3 squared, 1 is 1 squared. Is 10 double the product of 3 and 1? No. 6 is double the product of 3. If this were a perfect square trinomial, it would have been 9v squared minus 6v plus 1, minus 6v plus 1, which this is not. So instead, we got to do what? We got to break this thing down. This is either some sort of combination of 9v and v, or 3v and 3v. And we don't yet know which one. Honestly, I don't know which one yet either. Oh, now I do. Now, the good news is, good thing for this one, guys, is 1 is only a combination of some form of 1 and 1. So it's either this answer or this answer. Now, which one works? 9v times negative 1 is negative 9v, and that's minus 1v is negative 10v. So it looks like it's this one right here. So thankfully, that one did factor. Now, you know what? It can't be this one, because what do we say about this? 3v minus 1, it's not a perfect square trinomial. So I guess it couldn't have been this anyway. I guess you're only left with one option there once you recognize it's not a perfect square trinomial, and you're lucky that 1 was a nice, cleanest prime number in the world. You don't have to even reverse signs. All right, 21, 16b squared plus 70b plus 49. This is 16 is 4 squared, 49 is 7 squared. Is 70 double the product of 4 and 7? 4 times 7 is 28, doubled is 56. No, 70 is not 56. This is not a perfect square trinomial. Are there any common factors, by the way? That's always something to play with here. 49 being an odd number, no. So with the 16 here, that's going to be some combination of either. And this is where things get a little kind of hard. It's 4b and 4b, or 8b and 2b, or 16b and 1b. Thankfully, 49 it's nothing else but 49 and 1, or 7 and 7. So we know that there. It's either some form of that. But I also know which one of these it can be here because of the even linear coefficient. And if you heard me before, 49 being only odd factors, 49 and 1, or 7 and 7, that the only way to get this is from odd plus odd, which we can't get because we at least have a single even coefficient, or even plus even. And you can't get even plus even when we have, I guess it could be 8b or 2b, I'm sorry. We couldn't get it with 16b and 1b, because 1 being an odd number times an odd would give me an odd. So I'm going to leave that one out. Can't be this one. It's either 4b, 4b. Now, we know since it's not a perfect square trinomial, it's not going to be plus 7 because that would have been a perfect square trinomial. So the only chances if one of these is 49 and 1, well, will 4 times 49 give us something near 70? No, so it's not that. So it's either 49 and 1, 1 and 49, or 7 and 7. It's not going to be a 49 over here. 8 times 49 is just way too large. Definitely not that one there. We can try this one. 8 times, this is worth it. Oh, 2 times 49? Never mind. 2 times 49 is too large there. The only chance is if this is 7 and 7. 8 times 7 is 56. 2 times 7 is 14. 56 plus 14 is 70. All right, so that one worked out there. So it's going to be 8b plus 7 times 2b plus 7. So yeah, we had to factor, and look, listen, there's no way to not factor that out, but my point is you want to see if that was a perfect square trinomial first, because that would have been so immediate. So again, I'm trying to prove my point of saving you time when we can. I'm not going to stop trying to convince you of that. I legit am trying to do that right now. And 121b squared plus 132b plus 36. Well, this is 11 squared and this is 6 squared. If 132 is double the product of 11 and 6, then I'd be good. 11 times 6 is 66. You double that, yeah, you get 132. So you know what this is? 11b plus 6 quantity squared. I'm done. See how long this one took versus that one there? That's where this thing can be done fast if you recognize. Oh, by the way, keep forgetting to write the yes and no. Yes, this is a perfect square trinomial. No, this was not a perfect square trinomial. No, this was not a perfect square trinomial. And yes, this was a perfect square trinomial. All right, everything else I do here on out, these will be special cases. So if it looks like a perfect square trinomial, then it is. I mean, you have to set it equal to 0, of course, first before you do the factoring. Find greatest common factors first. But I'm going to go as fast as need be to now solve the rest of the way, because now we're past 30 minutes. All right, here we go. Number 23, 4n squared plus 12n plus 9 equals 0. Hey, that's 2 squared and that's 3 squared, and this is double the product of 2 and 3, which is 6 doubled is 12. So this becomes 2n plus 3, quantity squared equals 0. Now, if something squared is 0, then that means that thing is 0, right? The only way to get 0 is by squaring 0. So if 2n plus 3 equals 0, subtract 3 from both sides and divide both sides by 2, n equals negative 3 halves. There's only one answer to that. You know, sometimes there's more than one when we factor things that are different, but this is the same linear factor twice. So there's only one answer to that. In every perfect square trinomial, you're only going to get one answer for those, and negative 3 halves was the only value that makes that true. All right, 169x squared minus 4 equals 0. This looks like a difference of 2 squares. It's set equal to 0. There's no common factors. 169 is 13 squared. 4 is 2 squared. So this is 13x plus 2 times 13x minus 2. And that's set equal to 0. Now, the good news about situations like this is both these answers will be opposite of each other. So technically, in solving one, you kind of do solve the other. You'll see what I mean here. Either 13x plus 2 equals 0 or 13x minus 2 equals 0. Subtract 2 from both sides and divide both sides by 13. You get x equals negative 2/13. And then if you add 2 to both sides and divide both sides by 13, you get x equals positive 2/13. So once again, you'll see a plus or minus version. Sometimes you'll see x equals plus or minus 2/13, which is just saying that it's one answer or the other like that. You'll see instances where we start doing that when we solve using square roots, which is technically possible to do in a problem like this. But there it is, one, the other, both. All right, number 25, 98b squared minus 112b plus 32 equals 0. In terms of recognition of perfect square trinomials, I know these aren't perfect squares, but these are all even numbers. So, you know, you can factor a 2 out. So I'm going to go ahead and do that. A 2 can definitely be pulled out of here. And I do get 49b squared. 49 is a perfect square. That's 56b, and that's 16. It looks like those don't have any common factors there. 16 doesn't factor out with 7 like these do. 49 doesn't factor out with 2 like these do, or 4, or 8 like these do here. So that's the greatest common factor. 2 is no longer relevant to this. I can divide both sides by 2, and I have 49b squared minus 56b plus 16 equals 0. Okay, this is 7 squared. This is 4 squared. Is 56 double the product of 7 and 4? 7 times 4 is 28. Doubled is 56. So this becomes 7b minus 4 quantity squared. Again, that minus leaves us with that minus. So that equals 0. Therefore, 7b minus 4 equals 0. Add 4 to both sides. Divide both sides by 7. You get b equals 4/7. Just that one answer. Perfect square trinomials. If they exist, you factor it using the special case. Don't make it harder than it should be. Recognize it. Go to it. 32a squared minus 200 equals 0. Definitely a common factor of at least 2. I bet 200 can divide by 4, so that's even bigger. I hope there's something bigger, though, because 4, see, if I... Okay, I'll play with this in a couple ways. Let's say we only factored a 2 out. You get 16a squared minus 100 equals 0. And you know what? These are both perfect squares right here. You could actually use a difference of 2 squares here. If you were asked to factor this completely, though, and you got this as 16 is 4 squared, 100 is 10 squared, you did this right here. Listen, you can solve from here. This isn't unsolvable at this stage. You've created factorization, a product of things here, and set equal to 0, like that. But if you're asked to factor completely, this is not completely factored because 4a plus 10 and 4a minus 10 each have common factors of 2. So you can solve from there if 2 is all you did and you recognize that's a perfect, a difference of 2 squares there. But if you were to factor completely, if you were asked to factor completely, that's not a complete and full factorization. You can actually divide 8 out of these things here at most. If I factor an 8 out, I get 4a squared minus 25 equals 0. And these are still perfect square values here. Now, if I factored out a 4, I would have gotten, 8a squared minus 50 equals 0. And those aren't perfect squares there. So that's that weird in between. You factored not enough, too little, and yet too much. At least too little would have still gotten you something there. So the 8 is actually the preferred way right here because these are also perfect squares. That's 2 squared and 5 squared. So this becomes 2a plus 5 times 2a minus 5, like that. Divide both sides by 8, or either or. This is zero product property at this point here. Either 2a plus 5 equals 0, or 2a minus 5 equals 0. 8 doesn't equal 0, so I'll move on from that. Subtract 5 from both sides. 2a equals negative 5. Divide both sides by 2. A equals negative 5 halves. If you know what we did last time, that would mean a is positive 5 halves here. I don't even really need to show the work at that stage because it's just going to be the opposite sign value for a difference of 2 squares. All right, and 2 more problems here. 9a squared equals 64. Well, this isn't set equal to 0, so I can't solve using the zero product property unless it is set equal to 0. So I'm going to subtract 64 from both sides here. And then I get 9a squared minus 64 equals 0. Heads up, this is a difference of 2 squares right here. 9a quantity squared is 3a squared. And then, 9 squared is 3a quantity squared, and 64 is 8 squared. So this is 3a plus 8 times 3a minus 8. Set them equal to 0. If 3a plus 8 equals 0, I'll let you do the grunt work there, but that's negative 8 thirds. Or set that equal to 0. A is positive 8 thirds. Set them equal to 0, of course, and then solve for those. That's what you should get. Sorry, just my time. For time's sake, I'm going to keep moving on. And lastly, number 28 here, not set equal to 0 again. This equals 50v. Let's go ahead and let's subtract that 50v over, and of course combine it with the other. It's apparently another negative 50v. 50v minus 50v is 0. These don't cancel. That's negative 100v. Be careful on that. So 125v squared minus 100v plus 20 equals 0. I don't see perfect squares here, but that might mean we're looking at common factors, and I believe we are. These can factor out of 25, but 20 can't. I could probably factor a 5 out of these at most. So I factor 5 out, I get 25v squared minus 20v plus 4 equals 0. All right, that's more like it. 25 is 5 squared, 4 is 2 squared. 20 is double the product of 5 and 2. 5 times 2 is 10, doubled is 20. Or negative 20 there means that we'll have 5v minus 2 quantity squared, like that. The 5 is irrelevant to this case. If 5 times something is 0, then that something is going to have to be the thing that's 0. 0 squared is still 0. So the whole case here that we're looking at is if 5v minus 2 equals 0, what is v? Add 2 to both sides, divide both sides by 5, v equals 2 fifths, like that, right there. And that's the final one. So we're dealing with special cases there, guys, or sometimes not special cases, recognizing what they are, and you can see how they can quicken up your workload, especially when the numbers get big and huge. And if they are not, then how long they'll have to take for you to do, whether you don't recognize it or whether there's not perfect score trinomials or what have you, and how we can then solve them by factoring in the same way as before. And I promise you guys that it's not just a process for speeding things up for us. There are bigger uses, bigger and badder uses to this that you're actually going to see, at least for perfect score trinomials, within a month or so, as far as completing the square and what we do with that. So it's still relevant to what we do. You still got to recognize what's going on there. So that'll do it for this one, guys. This is Mr. Robinson. Thank you so much for watching, and I'll see you in the next one. Take care.